We're checking example 4, section 5.3. So this is talking about the concavity of a graph. So hopefully we've read about what concavity is in the book and watched the videos, etc. So this is pretty similar to what we had been doing about determining when a function is increasing or decreasing, except now instead of using the first derivative, we're using the second derivative. Make sure that we can see this. So first thing we'll want to do is find the first derivative. We get 5x to the fourth power minus 90x squared. And then we need the second derivative to determine the concavity. So again, this is very similar to what we had done with increasing, decreasing functions. Now we're using the second derivative instead of the first. Okay, so there's the second derivative of this function. Now we're going to do pretty much everything that we had done with the first derivative in the previous section. Now we're going to do it with the second derivative. Okay, so that means we set it to 0, but before we do that, let's go ahead and factor this a little bit. So we can factor out a 20x, and if we do that, that'll leave us with x squared minus 9. Okay, and then just like we had done with the first derivative, we're going to set that equal to 0. Okay, so we set that equal to 0, and then we'll set each factor separately equal to 0. Solve each of these. So this gives us x equals 0, and this one we can either factor it or move that 9 to the other side and get x equals 3 and x equals negative 3. Okay, so now what we should notice here is that these are not critical numbers, but they act like critical numbers did when we were talking about the first derivative. These are places where the second derivative is 0, and hence they are also places where the second derivative might change sign from one side of this number to the other. So what we call these are possible inflection points. And if you've read the section about this, inflection points are where the concavity of a function changes. So these are possible inflection points, and that means that they occur at these x values, at x equals minus 3, 0, and 3. Okay? So now, in order to determine if they actually are inflection points, we have to then see if the sign of the second derivative actually changed or not. So we'll set up our table just like we did before with the first derivative, only now, again, we're doing it with the second. So we'll go from minus infinity up to minus 3 up to 0, 0 to 3, and then 3 to infinity. Okay, and we're going to do this same way that we did with the table with the first derivative, only now we're doing it with the second. So again, we have test values. Now the second row is where things change a little bit. Now we're interested not in the sign of the first derivative, but in the sign of the second derivative. And then here we draw our conclusions based on that. Now remember, the concavity is positive, it's concave up in other words, if the second derivative is positive, and it's concave down if the second derivative is negative. That's why we're making the table like we are here. So let's pick our test values. We'll pick minus 4, pick minus 1, we'll pick 1, and we'll pick 4. Okay, so now we're going to plug all these test values up here into the second derivative. I'm going to use this factored form of the second derivative, almost fully factored. So let's see what happens. If we plug in negative 4 here, what happens? Well, negative 4 squared is going to give us positive 16, and so this term right here will be positive. But since I have a negative there on that x, the whole thing will be negative. Now when I plug in negative 1, what happens now? Well, negative 1 squared is positive 1, minus 9 makes this term now negative, but then that term is also negative, so negative times a negative gives us a positive. When I plug in 1, now that term is positive, but now that one is negative, so I have a negative. And then finally, when I plug in 4, that's positive. 16 minus 9 is positive. That's also positive, so we get positive there. So what is our conclusion? Our conclusion is that the function is concave down on that interval, then it's concave up on the second one, and then it's concave down, and then it's concave up. Notice that our conclusion row is different as well. Previously, if we were talking about increasing, decreasing, we would have put an up arrow, down arrow. Here, concave down, if you want to, you can also put a little sad face, and then for concave up, smiley. If you want to do that for concavity, that's fine. Okay, and then so it says to find all of the inflection points. So to do that, we need to notice that concavity did change on either side of this magic number here, the place where the second derivative was negative, or sorry, was 0, at 3, 0, and negative 3. So concavity did change, so that means we do have an inflection point. I'm just going to abbreviate that with IP. So we have inflection points we have 3 of them, in fact, because concavity changed here and here and here. So where are they? Well, they're at negative 3, f of negative 3, and then we've got another one at 0, f of 0, and then we've got another one at 3, f of 3. Okay, so negative 3, f of negative 3. For that one, we're going to have to actually plug negative 3 into this function here. Now, I don't have my calculator with me today, so what you would have to do is you'll have to plug that number into here, x to the 5th and x to the 3rd, and simplify that, and that will give you the y value there, and you'll actually need that y value. And the same with 3. If you plug those in there, you'll find some number, that will be the y value they put there. This one we can actually do no problem. So that's at 0, 0. Like I said, sorry about the calculator thing today. I don't want to do that in my head right now, so just plug the negative 3 into the original function, plug the 3 into the original function, find those y values there, and that's what you're looking for the exact location of these inflection points. Okay, and that's what you'll have to do in my math lab as well.